Welcome everyone to my presentation about Project Loom. This is a project that's been around for at least a couple of years, of what I know. And it's mainly about adding lightweight threads to Java, which was, well, a feature that's been in other programming languages, but still in Java, we didn't have it yet. Maybe with some libraries, but you'll see. All right, so I'm gonna start with some basics, and let's think about the beginning. In the beginning, there were processes, and you could think of processes like a single thread back then, and they all had these, let's say, components. First, there's the process internals. So it has an ID, it has some file descriptors, it has some window handlers or anything that a process may need to work inside with things that we don't care about, but they're there. And then there's the code of the application and the memory that's allocated in the heap. And the thread usually has its stack with the parameters and the functions that are called, and it has the registers which are responsible with calculating in the processor. And usually, if you want to have something in parallel computed, you would instantiate another process, and that process would take another set of internals. It would have its own code, of course, and it would have its own heap. And the first revolution was to create multi-threaded processes. So the thread became the main unit of computation, and you would have two tasks ran in the same process, and they would share the same process internals, the same code, and the same heap. So there's a lot of optimization. And that went well, and it scaled well until it didn't. And it didn't when we wanted to instantiate a lot of threads just to wait for things. Now, for this, there have been, in many languages, there have been implementation of lightweight threads. In Java, there hasn't been any of what I know, but in Scala, the language in which I currently program in, which is on top of the JVM, there are some libraries that implement this lightweight thread mechanism, like CATS or ZIO. And how this works is usually you use this library. You're defining your tasks and pieces of tasks, let's say, and you give those tasks to the library to run it on lightweight threads. This is a simplified view, but we'll see. Now I want to talk about something equally important, and that is waiting. So for multiprocessing, performing a sync call or a sync operation that waits is problematic. So think about this. Think about here. In the beginning, there were booth telephones, and there were persons waiting in line to talk at that phone. Now, imagine if that lady would wait for the other person on the other side to respond, and it would just call and wait for responding and just wait. The other person wouldn't get their share of the telephone. And this is similar to what happens in an application when you don't take syncing into account. And this problem appeared pretty soon, because let's think about Java. Here in the platform, you can do all sorts of things that block the current thread. First, it's taking the time, asking for the time. current time milliseconds is gonna wait for the results of the clock, the machine clock. And then when you print something, you would say that it's instantaneous, but it's not really instantaneous. So you wait for the thread waits for the buffer to write for the writing confirmation. And also flush, I should have added it here very well. Also, when reading from a socket, from a file or anything, the current thread waits for reading that byte or that array of bytes and just leaves the thread in a waiting state, doing nothing, wasting resources. And for this, multiple solutions were implemented, or mitigations, let's say, and they all have something in common, which I've heard in the specialty vocabulary called async barriers. So they all have in common this. After the task does some CPU work, before it's going to wait, it will be transferred on a different thread pool, which is filled with threads that wait. And other tasks will continue in the main thread pool to do their work. And then when one of these threads says, okay, I'm finished waiting, I've got a result, it's gonna move its work back to the main thread. Usually in the main thread, you have as many threads as CPU cores, because more than that, it's not useful to compute. And the waiting thread pool can have virtually unlimited threads. Okay, ways to implement this. The first and the most basic way is callbacks. You've seen callbacks before, I'm sure, and this on the left is some code from one of my hobby applications in Android, and this was Android, well, back when Java was the main language. And you could see here that I already have 2 levels of callbacks. The mechanism is simple. You make a call to a service, then this call will schedule on the waiting thread pool a task to wait for the call to return. And when that waiting thread finishes, it's going to continue with what's put in the callback. And this is pretty easy to implement, but it's not very friendly for the programmer, because you have to take care of a lot of things. Like, you don't have return, this function doesn't return anymore the result. It returns just something that, a confirmation, let's say. And then the scope of the variables, you may not see it here, but it's hard to put a hand on the variables if they're not final. But other ways of implementing async barriers have risen up, like generators. This is a code in JavaScript. And usually when you have function with star, this means that the function does not return a value anymore. It returns, when you call it first, it returns a user's generator, a generator with that function's execution. So every time you call next, it's gonna progress until it finds another yield. Yield meaning that I'm gonna stop the execution here, return from this function, and next time it's called, continue from here. And what this helps with, in this case, is that if you have a call for, let's say, to an endpoint to get something, after you do the call, you yield, and in the callback of that call, you can continue the execution from here, and the for is sequential. You assure sequentiality here. Okay, so still not very friendly for the programmer, but it has some advantages. And then there's what I worked with from time to time, Zio. This is one of the libraries I've talked about in Scala, and it has the concept of fibers. Fibers are when you suspend, this is the word, you suspend a side effect into an IO. This IO means that it's wrapping this so it can execute it somewhere else in the runtime. And afterwards, when you need the result, you call join on that fiber. The result is a fiber. Okay, and all this is a buildup of a program that you're going to execute. And the library then asks for this composed program to be submitted to its runtime. Once you do this, it's going to schedule all this work, the forking and other stuff until the joining on its thread pools. And it does some magic so that when this happens, the read, it's going to not use so many threads in the back. It's going to do some magic in the back so that it's when it returns, it's going to not use so much computation, let's say. Okay. But before I get to the critique, I want to say this disclaimer. The following slides and critique are not meant to propose replacements for those libraries. Rather, take them as libraries that will benefit from this project, and it may simplify their internal implementation. So that being said, with what price do we have these async barriers? First, no matter how much you optimize, you'll still need some threads. Even Zio needs some extra threads to do the waiting, even though they're optimized. And there's also, this means that there's a penalty on context switches on the CPU. And tasks need to be pushed around threads. They have to be kept track of. Usually I like to look at this picture and see when you look at the application, you see the UI and you think in the back it's happening with some magic. But what the library sees is some spaghetti there, some threads that this needs to follow now, this stopped waiting, this started waiting, and so on. Yeah, not very nice for the processor, I think. Okay, so let's see how this works in practice. So as an experiment and for comparison, I've proposed to create a cached thread pool. This one will instantiate threads as needed. And I'm gonna tell it to instantiate 40,000 threads. I pushed the limit there. And each thread is just going to wait 60 seconds. Okay, and I'm using the project Loom binaries just for comparison, but I'm going to run the application through a batch file because it's using that JDK. Okay, and now it's running. And as you see, now it starts to degrade in performance as more and more threads are instantiated. It gets slower to create new threads, and it consumes a lot of CPU. This is a beefy CPU, so on your normal day-to-day computer, you may see it even higher in usage. And yeah, you can see here that the number of threads is 40,000 and something. Now, the memory is up by 2 to 3 gigabytes just for having some threads that wait. And that is a lot because each thread has its own stack and its fixed allocation. So it will take that memory either way. Okay, so now since the 60 seconds have passed, the threads are starting to tear down. Of course, they're well, they suffer from performance degradation as well, and you can see that now, yeah, they're still hanged. They need to tear down. So that's another thing that I've realized that threads require. They need to tear down, and surprisingly, this takes even more CPU than initially. And that's a high cost, I think, for having threads. And of course, not reusing it. But this is a case that's, let's not say so common to have 40,000 threads, but in a normal application server, this is not out of the ordinary, except especially if you have IO intensive work. Okay, well, I'll leave it to tear down and continue with the slides. Okay, and what did they do first? In the first take, let's say, of Project Loom back in 2 years ago or more, they said, we're going to implement the same thing. We're going to implement fibers, continuations, like we saw in the other languages. And we're going to have our own platform, operations, and we're going to use our own collaborative concurrency mechanism, yield, like you saw with the generators. And they implemented that, and they tried it with starting to program using the new mechanisms. And what they saw is that they had the same problems, which they were not, they didn't like to add them. Like the return types, they would get tricky. Once you call a function and it's performing those asynchronous mechanisms, they're not, the method is not going to return the result. It's going to return a wrapper for that result. I've written completable future here, but well, this is just like something that would take the placeholder of a wrapper. Then they looked at other places. In Scala, if you use Zio or cats, you'll have to wrap your results as well. Even more things to specify in Zio, but that's due to the way it's thought of and its functional programming style. Then they looked over the fence at C# and they saw that when you have an async function, of course, you need to have the result wrapped in a task. The same thing, same problem they ran up into. And then they've realized that it's harder to debug an application because now you've got so many things that are escaping into the runtime, or at least not from the runtime to the language, that they need to be in the code. And when you step through them, you would get into unknown places of your library or of the implementation. And they didn't want to have that complicated stack trace and stepping in. And then there's the fact that you have to migrate your code. The old code, which does not take into account asynchronicity, it's not going to work so well. So if you have unguarded sleeps, writes, anything, you can get into messy things. And this can happen in your code. Maybe you can migrate it, but if you use things like proprietary SDKs, you can have some hidden wait logic there. Let's think of an example. You don't want to get into situations like somebody asks, why is the website down? And why are the servers up and waiting instead? And then you would look in the application and you would arrive at the conclusion that the bank's SDK has some retry logic and it's just waiting there because unguarded. And that's part of the proprietary SDK and you have nothing to do about it. So that's a situation in which you don't want to be. And even so, if you're eager to, well, let's say you, for every SDK call, you wrap it into something that puts it in a waiting thread, then you may have CPU work there and it works. It's going to hold the waiting thread and it's going to go over the other CPU intensive threads. And that's not great either. Okay, so after this, they said, no, we're going to start from scratch and we're going to call it differently. We're going to call it lightweight threads or virtual threads, and they're shifting names, but the idea is this. They thought, why bother the programmer with handling blocks in the language, in the application, when all the blocks are occurring in the platform? You've got waitings when a thread sleeps or an object waits for a notification. So except if you do funny things like while through and or you're calling native code outside of the platform, then everything comes down to what Ron Plessler said in one of his posts about the state of Loom. And I quote, whenever you run a blocking operation in, say, Spring or Hibernate, it ultimately makes use of some core library API in the JDK, the java.something packages. So, sure. And the chapter in which he said this is named, All Your Blocking Are Belong to Us. And it's no error. I've searched it on the internet, and this is an old meme, a bad translation from a video game. But they chose it very well because indeed the blocking is all in the platform, and they're in control of that. I mean the developers of the JDK, the OpenJDK. And they thought, well, if conceptually you do the same thing with a lightweight thread as with a normal thread, like running code, sleeping, waiting, interrupting, why then not use the thread API? And thread is an object since Java first, I think. And now it has this cool method called start virtual thread, and you give it the work inside. And of course, backwards compatibility, something we're used with in Java. If you start a virtual thread, then okay, but if you want to start a platform thread, you have a corresponding method for that. And if you start a thread the old way, then you have backwards compatibility to a platform thread. Notice that now the normal threads, heavyweight threads, they're called platform threads. Okay, and they started implementing what they wanted to have. First, sleeping. When it gets to the point of sleep milliseconds, this internal method in the JDK, they now dispatch and check if the thread is a virtual thread. You can see that it's what I post here is probably not what's now. There's room for improvement. You don't need to do this reflection. Then they do a vthread sleep. This means that it's a different kind of sleep for virtual threads and also for waiting on a lock. They check if the thread is virtual, this new way, and then they do a managed block. And what I think, although this is speculation and take it as is, they move it to a waiting thread because that's the usual mechanism. And I think this mechanism of managed blocking is going to be improved through time. But until we have some specific things, it's all subject to change. Okay, and then executors and thread pools. These have their own version of virtual threads. So as we had the cached thread pool, there's a virtual thread executor, which actually does what you would expect. It creates an unlimited number of virtual threads, unlimited by the computer you're on. And the first question that pops in mind, at least for me, is, can I substitute cached thread pool with a virtual thread pool? And that's actually the whole point. The idea is to have in one single line of code a change to lightweight threads and not having anything to change else. And it's easy to demonstrate this. Okay. Oops. Now in my demo, I'm going to substitute the executor service with a virtual thread executor. Nothing else that I need to change. And then now I see that it started the threads, and now you see that they are virtual threads. And they got pretty fast to 40,000. There was no performance degradation in starting them. There's also no number of threads here. They reused the usual main threads, and there's no memory overhead. It's just some, I think, less than hundreds of megabytes of overhead. Compared to 2 or 3 gigabytes like for usual platform threads. And yep, less context switch. There's less CPU usage in here while they wait. The great thing is that this just works like before. And now they're tearing down. The same thing, no performance degradation, and now it's just the application stopped. No need to tear down anything complicated. So it sounds too good to be true, almost. Let's recap. Now, in a usual code, like I've taken the JavaScript code and transferred it into a Java code with Project Loom. You don't need any more complex return types. It's just gonna return the list of your users. Then you don't need to care if an operation is async or not, because even if it's gonna call something synchronous in the back, it's going to get to something in the JDK, and the JDK is going to take care of not running it synchronously. So that's not needing to care anymore is a great thing. It's just going to move it automatically between the pools, the hypothetical pools, let's say. And then for stack traces, they've rewritten the debugger so that they just need they just output a normal stack trace. It didn't need much change, but in the end, you don't need to step in through some, cumbersome details when you have exceptions. And I like to compare this Project Loom implementation with the concept of sleeper cars or sleeper PCs. It means when you have an old-looking PC, nothing interesting about it, and then you open it up and you have some cool mechanisms inside, cool stuff, and super performant. And that's what I think Project Loom is going to make Java look like. Okay, and all this is good, but with a small caveat. And it's not like a star in which you read a lot of stuff underneath the fine print. This has been the caveat for lightweight threads, because unlike platform threads, they don't have preemption from the OS. This means that no one is going to take a lightweight thread from your application and move it away from the processor in your application just to make way for others. So if there's a lightweight thread that's CPU hogging, it's taking too much on the CPU, like I exemplified in the phone booth example. This is going to take all the CPU, and you don't have any mechanism to prevent the starvation of the other lightweight threads. And you solve this as you would solve without lightweight threads. You have to separate the CPU-intensive threads from the IO-intensive threads. You have different thread pools and schedulers for different types of load, but usually, as an example, if you have 8 cores and you have CPU and IO intensive, I would say reserve 2 for the IO intensive work, and then the others for the CPU load. And it should work fine, it should scale fine. So for CPU intensive work, the platform threads are good enough as always. And then maybe another question pops up. This sounds pretty good, but is Project Loom becoming a real thing? Is it going to go in the mainstream JVM? And the answer is, I think, yes. And the signs are that that's where it's heading. You see on the Inside Java blog, you see a person in the development doing a presentation every month or so. And in the GitHub project, there are daily commits, at least in the day I made this slide. Then one day, my friend Micha sent me a message, and she said, hey, Andrei, maybe you already know this, but there are some projects that already use Loom, and they use those early access builds. And I didn't know, actually, and I sent her my kudos for this and for these slides. I've been surprised to see that pushing some early builds already made some projects have their own branches. Like JUnit 5, it has the JUnit 5 looming fork, and they already posted some benchmarks. I thought first these are seconds, and it's taking 5 times less, and for many virtual threads it's taking even a lot less, but they are benchmark scores, and I don't know what those mean. But as you can see, it scales a lot better than threads, which is expected. And then there's Jetty, the famous application server. This one is going to, it has a branch called Jetty 10 Loom, and it's gonna implement the Loom, lightweight threads in its threads for handling requests. And I think for application servers, this will be a big selling point. I mean, all of them should have support for this. Imagine the first server saying that our server is 10 times, 100 times better than the previous version. If you don't ask how they did it, you would think that it's some weird magic, but it would have Project Loom, because this is the scalability of lightweight threads. Then there's Helidon. which is a collection of Java libraries for microservices. And they, in their last version, they posted support for virtual threads if you're using the early access builds of the project Loom. Okay, and also John DeGose, he's the author of the Zio library for Zio enthusiasts. In Zyverge, in the Zyverge site, his company where he is CEO, he posted that he's going to do a presentation. I didn't catch that presentation, unfortunately, at the end of 2020. And he presented how Project Loom is going to help improve the Zio library. He also posts on Twitter from time to time about Project Loom, and I like this one, how he observed that the Project Loom creators shifted to naming it virtual thread because Fiber doesn't say much, but virtual thread says that it's a thread and it's something virtual about it. So there's a lesson for the observant. Okay, and this leads me to the conclusion that you should expect to see Loom in an upcoming Java version, maybe 17, maybe 18, or who knows. But it's definitely gonna be a thing. All right. And now let's see if we have questions.
We definitely have questions. Okay, so maybe just to summarize a little bit, in terms of using this feature in current project, what would you recommend? I mean, this is something that we're I don't know, just playing with right now, prototyping, and it's a thing that we can embrace in some way.
Sure, it's like the way I see it is that you'll want to adopt it. If you don't have speed, you lose to your competition, and you want to have support for lightweight threads. Like Jetty, you've seen that they already implemented that. They're taking a proactive approach, and as I said, if you don't do funny stuff like calling native code or blocking the threads or doing too much CPU work and you don't isolate it, then you would want to use it with care. But sure, you'll use it for IO intensive work. And for the other cases, which is the majority of cases and the usual enterprise application use case, you would just change the version of your microservice application, server application, and it would say, hey, flip this switch and it's gonna use lightweight threads and it's gonna work. And this is the magic. I haven't seen this and I would be very excited to see it in other languages, but it's a first in Java.
Okay, so from your point of view, that's highly recommended, right?
Sure, a big thumbs up for using lightweight threads, and it's easy.
Okay, okay. What's your next favorite after the lightweight threads? You're very passionate about it and enthusiastic.
Oh.
I'd be curious.
Yeah, I am very curious about how they're going to use it in Spark. I already think they are going to use it. I'm writing also data pipelines in Spark on Databricks, and this is for big data, a lot of multi-threading happening across machines, but also inside a machine. And I'm curious that if they're gonna launch version 4, and that's gonna have lightweight threads, and what's gonna be the performance on that one. That's something that I'd like to see. yeah, and about my passion on threads, I like my phone to program it and tinker with it. And who knows if they're gonna put it on Android.
Yeah, good. We'll just have to wait and see. There are a couple of questions from the audience. I think you pretty much touched on them in your previous answers, but maybe just to recap. So one of them is, are you planning to use the project Loom in a side project for now and observe the changes, or do you feel confident in maybe using it further in production?
Not with early access builds. I wouldn't use early access builds in production yet. When it's in the released phase, I would use it in production. I like about the Java ecosystem, or at least the Java, how well Oracle is developing the Java platform. I like that they like to be sure when they launch something that it's compatible. And I'd say, why not take advantage of that? Start using it when it's ready. But for side projects, of course, use it, play with it, be ready when it's going to be launched.
All right, thanks. And yeah, when would you use normal threads and when virtual threads? Again, you briefly mentioned it before, but just to summarize.
Sure. The main takeaway is CPU work, platform threads, I/O work, lightweight threads. You've got plenty of executors, schedulers, thread pools to fit your load.
All right, perfect. And yeah, it's I think not a question. Somebody states here, and that's what we want to say. That was absolutely brilliant. Thanks, Andrei. So it's not just from us, also from the audience.
Well, thank you. Thank you for attending.
Can you hear people clapping? Or okay. It's just in my imagination? No,
no, I heard it from here.
Okay.
Okay. Yes. Thank you for having me here.
Super. So speaking of, I mean, the reason I wanted to ask you about your passions because it was like a subtle question about your next presentation, you know, not asking for commitments, you know me, but, you know.
Sure. And a bit of pressure is not actually harmful. And
it's not pressure at all, trust me, no.
Okay.
But see you next time, right?
Sure, definitely. I'm looking forward to doing another presentation. If I find something interesting about multi-threading, okay. If not, then there are some other things that are in the queue. I mentioned big data. I also think I mentioned phones, but other things as well.
Excellent.
Thank you very much, Andrei.
And you just set some expectations, so we're eager to.
But no pressure. But no pressure.
But no pressure at all. Okay.
None felt any.
Okay, Andrei. Until next time, then. Thank you so much, everyone. Sure. Let's have a break. 15 minutes.
Let's have a break. 15 minutes, and we get back. See you soon.
Bye.